Okay, first of all, I'd like to thank Johanna and her team for this great conference and for the invitation. So I'll be talking about work done with the collaborators listed here, some of which are present in this conference. So the context of this work is the quantum non-equilibrium physics of strongly interacting many-body systems. And a lot of the progress in this area has been driven by experiments in the context of ultra-relativistic heavy ion collisions, of cold atom systems, and of ultra-fast techniques in condensed matter physics. And it's the latter that will be relevant for this talk. So on the theoretical side, a challenge is the strong entanglement in these many-body systems. And the fact that these systems are strongly coupled is a motivation to use holography, and holography has already been quite successful in situations near equilibrium. So what is pump probe spectroscopy? Well, you take some sample of material you're interested in. This could be some high-TC superconducting material. You kick it out of equilibrium by some pump pulse, which will take to be some laser pulse. And then you probe the system, possibly by a second laser pulse. In our case, it will be used to measure conductivities as a function of time. So let's first talk about this setup in a context of zero density. So we start with a vacuum state or a thermal state of the system, and then we pump it out of equilibrium by a laser pulse. So this is some homogeneous pulse of transverse electric field. In this situation, at zero density, the setup is holographically dual to a Vaidia geometry, which represents a light-like shell that collapses and forms a black hole. Now, it's been known for some time now that one-point functions and retarded two-point functions, and conductivities are retarded two-point functions, assume their thermal equilibrium values immediately after the pumping of energy has ended. Now, this immediate thermalization might sound confusing when you first hear about it. So let me say a little bit more about it. So from a bulk perspective, it follows quite directly from causality in this system. So here is the light-like shell that excites the system. Now, if I perturb the system by a probe pulse after this injection and then measure what happens later on, by causality, everything that happens here is only sensitive to the geometry outside this light-like shell. And this is exactly a black brane geometry. So for these observables, the system is equivalent to a thermal system. Now, from a field theory perspective, it's a bit less straightforward. And okay, the best intuition I can offer are discussions of quantum thermalization, where the idea is that the information about the initial state gets spread into or gets encoded in the entanglement between degrees of freedom at the location of the observer and other degrees of freedom in the system. And this can happen quite fast in a strongly coupled setup. So these ideas are quite close to eigenstate thermalization hypothesis and things like that. Now, it's also clear that there should be other observables which do not assume their thermal values instantaneously. And that's the case if you look at non-local observables such as space-like two-point functions or entanglement entropy of spatial regions. One indeed finds that those do not thermalize instantaneously. But importantly, there are important physical observables such as conductivities that do thermalize instantaneously. Okay, now let's introduce a new ingredient which is important if we want to make contact with condensed matter physics, which is non-zero density. So we'll model a 2+1 dimensional strange metal found in high-TC superconductors by turning on a chemical potential. We'll apply, again, a pump laser pulse, so some short, spatially homogeneous transverse electric field pulse. we'll probe the time evolution of the optical conductivity in this model. And in order to have finite optical conductivities, we need to break translation invariance. We'll choose to do this in a very mild way, so the system will be almost translation invariant, and we'll use a very simple mechanism using linear axions that was introduced in this paper, and there were several related models in the literature. Now, before getting into any details, let me tell you what the main result will be. So the thermalization of the optical conductivity will continue to be instantaneous in this model, except if the pump pulse has a DC component. Because if it has a DC component, this will set the charges in motion and introduce a momentum density in the system. And because translation invariance is only mildly broken, it will take some time for this momentum to relax. Now, what is the mechanism behind this instantaneous thermalization? Well, roughly speaking, the deviations from equilibrium will be of the form some amplitude times an exponentially decaying function. And in the absence of a DC component of the pump pulse, it turns out that the amplitude of this deviation will vanish. So it's not the case that this decay constant tau will be small. Tau will be large as usual because momentum is almost conserved. The point is that you simply don't excite this mode because it has zero amplitude unless there is a DC component in the pump. So now let's introduce the model. So the context is Einstein-Maxwell theory coupled to some scalar fields called linear axions, whose purpose is to break translation invariance. So this system has equilibrium solutions. So they're basically Reisner-Nordström strange metals with some momentum dissipation. So the metric, the gauge field, and the scalar fields are written here. And we will want to excite this material by applying some time-dependent electric field, which will represent a laser pulse. So for this, we follow an ansatz made by Withers, who was studying related but different quantities in precisely this setup. So we introduce some metric functions called f and b. The electric field pump is encoded in the near boundary behavior of the gauge potential, and we'll also have to allow some fluctuations in one of the scalar fields if we choose an electric field in the corresponding direction. So we will choose to focus on electric field profiles that mimic as closely as possible a laser pulse. So let me discuss it on the next slide. So we will want the pulse to oscillate in time. So there's the cosine you see here. Omega p will be the central frequency of the pulse. We want the pump to last for some finite time. So for that, we introduce this Gaussian modulation, this Gaussian modulation in time. And in order to be really sure that we can consider the pumping to have ended at some certain time so that we can ignore the tails of the Gaussian modulation, we introduce this resolved step function at 3 standard deviations so that after that, we're really sure that we can ignore whatever is left from the source. So I've drawn 3 cases which differ by the frequencies. So here they are as a function of time, and here are the Fourier transformed versions. And what will be important is the question whether the Fourier transformed pulse contains significant contributions from zero frequency. So this will obviously be the case for this pulse. There will be some contribution for the next one, and this one has negligible contribution at zero frequency. All right, so as I mentioned already, at zero charge density, we would have a simpler Weidja geometry, which would immediately imply instantaneous thermalization, etc. If we introduce momentum dissipation before introducing non-zero charge density, not much would change. There are explicit solutions that do this, and they're also widely alike. So at non-zero charge density, things get more complicated, and numerical GR is required. And the physical mechanism, as I mentioned already, is that the electric field in this case will induce momentum for the charges. This momentum is, of course, some component of the energy momentum tensor, and this will induce additional bulk, additional metric components in the bulk, which makes it the things more complicated. So first, let's look at the one-point functions in the field theory, which can be read off from the bulk solutions. What we will eventually be interested in are retarded two-point functions, but that will come later. So you can read off these one-point functions from some regularized bulk fields near the boundary. I'm not going to give the precise definitions of these regularized fields. And you find, for instance, for the case with vanishing pump frequency, where you have a strong DC component, that these components of the energy momentum tensor and the other boundary operators decay exponentially, most of them with some specific frequency omega I, and another with twice that frequency. And its frequency corresponds to the leading vector quasi-normal mode, which comes from the mild breaking of translation invariance. So there's one quasi-normal mode that will dominate the dynamics in this regime that we're studying. So this is a slow decay because this imaginary frequency will be quite small. And to explain the factor of 2 for this component, you can observe that the tensor mode B is sourced by the square of the vector mode F, so by the square of the momentum density, and that's why it decays twice as fast. So what you see when you run the numerics is that the quasi-normal mode amplitude, so the deviation from the equilibrium situation in this, for these various quantities, it doesn't matter what exactly is plotted, that these deviations become small as you increase the pump frequency. And that's something we can also understand analytically. So if you go to the regime of large pump frequency, you can do an expansion in 1 over that frequency. And from looking at the numerical results and staring at the equations, you can come up with an ansatz of how the various bulk fields scale with as a function of frequency to leading order, and then you can correct it at subleading orders. And when you do this expansion and solve the equations order by order in 1 over omega, you find to leading order precisely a Weidja solution, where the time-dependent mass function is given by the original mass function in equilibrium plus the energy that you pump in via the electric field. And the first subleading correction in 1 over omega would basically correspond to the momentum that was injected in the system, but this will be suppressed by 1 over omega during the pulse, and after the pulse it will be suppressed much more strongly, because if you look at this equation for large V, so after the support of these electric fields, and you remember that this is a cosine times something that varies very slowly, by basic Fourier analysis you see that it will decay faster than any polynomial in 1 over omega. So to get a sense for the amplitudes of these quasi-normal modes, one can make a linear response estimate. So this is some, standard linear response thing. So the response is given by convolving a retarded green function with a source. You can make a quasi-normal mode expansion of this retarded green function and do some integration by parts. And in the end, you see that the response is determined by the Fourier transform of the electric field evaluated at a quasi-normal mode frequency. And you can check that, although we're not quite in a linear regime, the linear response estimate for the amplitude matches very well the exact numerical behavior that one computes. Okay, let me not go into details, but this, for instance, is a one-parameter fit of the red data points. Okay, so now let's move on to the quantity that we're actually interested in, the probe conductivity. So we are not in equilibrium, so the conductivity that relates the electric field perturbation with the generated current will depend on two times, not just on the time difference. And in order to compute or measure the conductivity, one can simply choose a delta function profile for the electric field, or some resolve the delta function if you do it numerically, and then the conductivity comes out by measuring the current that comes out. So we have this conductivity that depends on two times. Now we want to define some frequency space version of it, and one convenient way of defining it corresponds to Fourier transforming the relative time while keeping the initial time fixed. And one can check that in equilibrium, this reduces to the well-known conventional definition. So this conductivity, it's an optical conductivity that depends on omega, but it's also, in addition, time dependent. So it will be an optical conductivity that evolves in time. Okay, so here is the main result for the optical conductivity. On the left panel, we consider the case of a pump pulse that has no significant zero frequency component. On the right panel, we do have a zero frequency component. This line corresponds to the initial thermal profile for the optical conductivity. And in the case without zero frequency component, you see that everything else, so immediately after the pulse, coincides with the late time thermal equilibrium distribution for the optical conductivity. In the case with a DC component, you evolve gradually from the early time results towards the late time results. So if the DC conductivity does not immediately take on its late time equilibrium value, you can check that it evolves, that it relaxes exponentially towards this late time value. And perhaps slightly surprisingly at first, this exponential decay is not quite set by the imaginary part of this dominant quasi-normal mode, but by twice the imaginary part of this quasi-normal mode's frequency. So let's go through the mechanism once again. So how can it be that this thermalization is governed by half a momentum relaxation rate? Well, I already mentioned the fact that you induce momentum, which has to relax. So the bulk interpretation of that is that in a linearized approximation, the decay would be governed by the lowest quasi-normal mode frequency. But then if you look more carefully, you can convince yourself that the induced momentum appears squared in the computation of the conductivity, and that's why the conductivity relaxes twice as fast. We also have some symmetry arguments to argue that this is indeed the case. So is this something one can measure? Because that was our motivation to relate these holographic stories of thermalization to something that can hopefully be measured not too long from now. So well, I think this fast thermalization, or essentially instantaneous thermalization, is something tantalizing to see if there is some reflection of that in realistic systems one can study in the lab. It's not completely straightforward, however. There are several complications. One is that We want to avoid high-frequency components in the pulp because the regime that is supposed to be described by holography is the infrared regime. We don't want to look at things that are specific to UV details of the model. Also, the characteristic time scale of the ordinary electronic relaxation processes are femtoseconds. So if you want to claim that something is anomalously fast, you should be sensitive to the relevant timescales. And well, from what I'm told, this is something the experiments are approaching quite fast. And you obviously need a very good time resolution. And okay, I think it's important to add this to the list of things where one can hope to try and test predictions that came out of holography in some real-life systems, which of course will not, well, will be different from holographic systems in that they have finite n and things like that. But there's other contexts, such as heavy ion collisions and minimal viscosity discussions, where predictions that came out of holography seem to do quite well in realistic systems. Thank you. So let me go through what I've told you once again. So we modeled 2+1D strange metals pumped out of equilibrium by some laser pulse, and we probed the optical conductivity as a function of time in a context with mildly broken translation invariance. At 0 density, we would have instantaneous thermalization. This remains the case at finite density if we don't have a significant DC component in the pump. If we do have a DC component, there is a slow relaxation, which is governed by a quasi-normal mode with an interesting factor of 2. So let me end here.